December 2025 now carries a warning from NOAA, a solar threat driven by the emergence of AR 4294, one of the most magnetically unstable sunspot systems of this cycle. If it releases a major CME toward Earth, the impact could rival the Carrington Event of 1859, and our electrical grid is nowhere near prepared for it. Just 48 hours without electricity would trigger a chain reaction across modern society. Water treatment shutting down, food distribution halting, medical systems failing, and public safety degrading in rapid succession. In this episode, we'll examine the science behind NOAA's prediction and what it reveals about the fragile systems we depend on. If this kind of grounded analysis matters to you, a like and subscribe go a long way. Let's get into it. Right now, as you listen, there is a feature on the sun's surface that has not appeared in more than a decade. It is a dark region shaped by magnetic disorder, large enough to hold about 10 Earths, with space still left around them. It moved into view only hours ago, as the sun's rotation carried it from the far side of the star. As soon as it appeared, monitoring systems across many agencies registered it, and scientists began paying close attention. NASA is watching. NOAA is watching. Every group that studies space weather is tracking this single area, because what follows could matter on a global scale. The region has been labeled Active Region 4294 through 4296, a structure so wide and complex that it had to be divided into 3 numbered groups. Reports from amateur observers say that with the correct solar filter, the feature is large enough to be seen by eye. It spans roughly 5 Earths in height and 5 Earths in width, and its position is now directly facing our planet. The question that many hesitate to ask is simple. What happens if it releases a major flare? What if the largest sunspot seen in about 10 years becomes active at the exact moment when Earth is in its path? Scientists are working to understand the risks over the next 72 hours and to outline what a worst-case situation could mean for the systems people depend on every day. To understand this region, it helps to look at the nature of the sun. Our star is not a quiet ball of light. It is a self-sustaining nuclear furnace held together by gravity, filled with plasma that moves, twists, and folds in ways that create constant magnetic tension. Temperatures at the core reach more than 15 million degrees Celsius, while the surface layers are shaped by rising and falling streams of charged gas. When magnetic fields become tangled, they change how heat flows, and dark areas, known as sunspots, appear. These areas look black only because they are cooler than the bright surface around them, usually near 3,500 degrees Celsius, rather than about 5,500 degrees Celsius. They are still extremely hot, more than enough to destroy any material humans have ever created. The sunspot that formed on December 1st, the region labeled 4294 through 4296, is far from ordinary. An observer in Santiago, Chile, described how its full structure required more than 2 days to rotate into view from behind the eastern edge of the sun. That long arrival hints at its size. She also noted the presence of a delta magnetic component. In solar physics, a delta configuration forms when magnetic fields of opposite polarity sit inside the same penumbral area. In simple terms, it is like seeing 2 opposing forces pressed tightly together. Pressure builds over time, and the system becomes unstable. Sunspot classifications help researchers understand risk. Alpha regions have one magnetic polarity and tend to be calm. Beta regions contain both positive and negative areas, but remain neatly separated. Beta-gamma regions show mixed polarities with no clean dividing line. The most complex type, beta, gamma, delta, shows opposite polarities packed together inside one shared structure. Active region 4294 fits this last category. In magnetic terms, it behaves like a spring that has been wound too tightly. This moment is important because it arrives during a very active part of solar cycle 25. When the cycle began in December of 2019, scientists expected a quiet maximum similar to the weaker cycle before it. They predicted a peak of about 115 sunspots around July of 2025. By 2022, it was clear the sun was exceeding those expectations. By 2023, NOAA raised its forecasts, stating that the maximum would come earlier and with higher activity. By October of 2024, data showed that the maximum might have already begun as much as 2 years earlier than planned. In August of 2024, sunspot counts reached their highest level since September of 2001. During this period, the sun has produced more X-class flares, the most powerful type. On November 11th, active region 4274 released an X5.16 flare, the strongest recorded in 2025 and the 6th largest of the entire cycle. The event sent out a coronal mass ejection, traveling at nearly 1,950 kilometers per second, fast enough for NOAA to issue a rare G4 geomagnetic storm watch. 2 weeks after that, another region produced several X-class flares in a short time, adding more signs that the star is running at a higher level of activity than the predictive models once suggested. Now, as this unusually large sunspot rotates into view, signs of activity continue. On the same day that region 4294 became visible, a nearby area labeled 4299 released an Exone 0.9 flare at 0227, Coordinated Universal Time. NASA's Solar Dynamics Observatory recorded the event as a rising structure of plasma and radiation. The flare's energy reached Earth in about 8 minutes, altering conditions in the upper layers of the atmosphere and creating an R3 radio blackout over Australia. For around 30 minutes, aviation and maritime communication in high-frequency bands became unreliable or stopped, all from an event originating roughly 93 million miles away. That flare did not come from the large sunspot, but from a smaller area, acting almost like an early signal of what the larger region might be capable of. Images from the Solar and Heliospheric Observatory showed a fast, partial halo coronal mass ejection connected to that event. It carried billions of tons of charged particles into space at high speed. The path did not cross Earth, which reduced the threat, but solar rotation continues to adjust the alignment. With every hour, the large sunspot turns more directly toward our planet. Forecasts from NOAA's Space Weather Prediction Center for December 1st through December 5th outline a high chance of solar activity, including a 70% likelihood of M-class flares and a continued possibility of more X-class flares. They also expect active to gone minor geomagnetic conditions around December 3rd as a high-speed solar wind stream passes Earth, the same feature that brought strong winds in early November. By December 4th, conditions could reach gone to G2 levels, and the planetary K-index may rise to 7 at peak. This could allow auroras to appear much farther from the poles, possibly reaching areas near Toronto, Chicago, Boston, and Melbourne. The displays would be striking, yet the forces behind them carry real concerns. The core issue is the magnetic structure inside region 4294. A delta configuration means it holds stored energy inside twisted loops of magnetic field. When those loops reconnect, the release can become a flare, able to send out energy equal to billions of nuclear detonations. X-class flares can disturb radio communication on Earth within minutes. More important, many large flares are followed by coronal mass ejections, These are not just bursts of light, but streams of charged particles traveling anywhere from 250 to more than 3,000 kilometers per second. They can reach Earth in under a day or take several days, depending on their speed. When such a stream reaches Earth's magnetosphere, the magnetic shield around our planet begins to respond. Under normal conditions, the shield guides most of the incoming particles toward the poles, creating auroras. But if the magnetic field carried by the stream is oriented in the wrong direction or arrives with enough strength, the shield can compress or distort. In stronger cases, more energy reaches the upper atmosphere, and the technologies humans rely on, power grids, satellites, navigation systems, and communication networks, all depend on stable electrical and magnetic conditions. Many of these systems were not built with severe solar storms in mind, which leaves a point of vulnerability. As this larger context remains in place, the sunspot continues to rotate, moving into a more direct alignment with Earth. People around the world follow familiar daily routines, unaware that a feature on the sun can influence systems on the ground. The next several days will show whether region 4294 is simply large or genuinely hazardous. Scientists hope for the more stable outcome while preparing for the other. Instruments in observatories across many countries continue to record every small change, watching for signs that magnetic tension is approaching release. The sun has begun December with a clear signal. Whether that signal becomes a warning or something stronger is still unknown. To understand why this position matters, it helps to look at what happened in the year 1859, when a similar magnetic arrangement on the sun triggered what is now called the Carrington storm. That earlier world lived by telegraph wires and gas lamps. It could not imagine how dependent future generations would become on technologies most exposed to solar activity. Today, the conditions are different. The systems are more complex, and the risks affect far more of daily life. The sun continues operating according to forces that do not adjust for human needs. When the sun released a burst of electromagnetic radiation at 0227 Coordinated Universal Time on December 1st, 2025, the energy crossed roughly 93 million miles of space in about 8 minutes and 20 seconds. By the time the first photons reached Earth, the event had already faded on the solar surface. But for the people on the sunlit half of the planet, the effects were only beginning. Australia faced the strongest impact. Across the continent, high-frequency radio communication failed almost instantly. Aviation systems shifted into static. Maritime operators lost contact, even though their equipment still functioned. For about 30 minutes, a modern nation experienced a sudden communications gap caused by an explosion on a star. This was an R3 event on the NOAA radio blackout scale, which ranges from Rhone Minor through R5 Extreme. An R3 event is considered strong, meaning wide area disruption of high-frequency radio communication on the sunlit side of Earth, along with navigation errors and degraded long-distance signals. It does not collapse infrastructure, and it does not threaten civilization, but it shows clearly how the systems we rely on operate under conditions shaped by space weather. It is a quiet reminder that our technology sits within an environment ruled by forces larger than any human design. The flare responsible for this disruption was classified as X1.9. It helps to look at how solar flares are categorized. The system uses the letters A, B, C, M, and X. Each step represents about a 10-fold increase in energy output. A-class flares barely rise above the sun's background radiation. B-class flares are slightly stronger, but still unimportant for Earth. Class flares are common and can cause minor interference near the poles. M-class flares are moderate, with enough strength to create brief radio blackouts in high-latitude regions and sometimes at lower latitudes. X-class flares form the highest tier, The number following the letter shows the intensity within that tier. An X1 flare is 10 times stronger than an M1, and an X10 is 10 times stronger than an X1. There is no upper limit. The largest flare ever recorded occurred in November of 2003 and reached an estimated X45, strong enough to saturate sensors. An X1.9 flare sits at the lower edge of the extreme class. It is strong enough to disturb radio communication and to change how radio waves move through the upper atmosphere, but not strong enough to threaten satellite health or electrical grids. The event over Australia represented a moderate solar outburst from a region that had only just rotated into view. The concern lies not in this single flare, but in what it signals. A new active region, still emerging from the far side of the Sun, had already shown it could produce X-class activity. Behind it, turning into a more direct position, rested the largest sunspot complex in about 10 years. The geometry of this movement matters. The Sun rotates roughly once every 25 days at its equator. Active regions appear, grow, and decay over days or weeks. As the surface turns, these regions sweep across the visible solar disk. When a sunspot sits near the eastern limb, it is pointed away from Earth, and any flare or coronal mass ejection shoots to the side. But as rotation carries the region forward, it moves toward the center of the disk. Once it reaches that central band, anything it releases is directed outward along a line that intersects Earth's orbit. Active region 4294 appeared near the eastern limb on December 1st. It will require about 7 days to reach the western limb. Around December of 4th or 5th, it will pass through the zone where any coronal mass ejection would be aimed directly at Earth. The X1.9 flare that caused the Australian blackout came from active region 4299, a smaller group moving a short distance ahead of the larger region. It behaved like a sign of what may come, a lighter event showing the sensitivity of the environment before the more powerful structure reaches its most effective alignment. The flare reached its peak at 9:49 in the evening Eastern Standard Time on November 30th, which corresponds to the early hours of December 1st in Coordinated Universal Time. NASA's Solar Dynamics Observatory recorded the flare using several wavelengths. In extreme ultraviolet views, the flare appeared as an intense, brief flash, standing out against the darker corona. Large loops of plasma rose high above the surface, shaped by magnetic field lines that became visible through the superheated material held inside them. These arcs reached hundreds of thousands of kilometers above the solar surface, forming an image of energy rising and falling through magnetic tension. The coronal mass ejection associated with the flare was recorded by the coronagraph instruments aboard the Solar and Heliospheric Observatory, often called SOHO. This spacecraft sits at the Lone Lagrange point, a location about 1.5 million kilometers sunward of Earth where gravitational forces keep it in a stable position. From there, SOHO blocks the bright solar disk and observes the fainter outer atmosphere. On December 1st, it captured a rapidly expanding partial halo around the Sun, which revealed that material was being pushed outward in Earth's general direction, but not directly toward the planet. Further study confirmed this. The ejection would pass Earth at a distance, missing the planet. That near miss still carried meaning. The speed of the spreading material showed high velocity, fast enough that, if directed at Earth, it would have arrived in less than 2 days. Fast coronal mass ejections demand attention. They compress the solar wind, forming shock fronts that increase the pressure on a planet's magnetic field. The fastest events ever measured reached Earth in about 15 to 18 hours. The coronal mass ejection linked to the Carrington Event reached Earth in roughly 17.5 hours. Most events take between 2 and 4 days. When a fast event appears, even one not heading toward Earth, researchers take notice. It points to active conditions and to the potential for more intense releases. The radio blackout over Australia also showed something important about the difference between flares and coronal mass ejections. Flare effects are immediate, but temporary. Electromagnetic radiation travels at the speed of light. By the time sensors detect a flare, its energy is already interacting with Earth's upper atmosphere. The resulting ionospheric disturbance fades quickly once the radiation stops. Communications return within minutes or hours, and no hardware is damaged. Coronal mass ejections are different. A flare is a burst of light. A coronal mass ejection is a stream of charged material that physically strikes Earth's magnetic shield. That shield, the magnetosphere, normally protects life by deflecting most solar particles toward the poles. But when a strong ejection arrives with the wrong magnetic orientation, it can compress the magnetosphere and push energy into the upper atmosphere. In severe cases, it can allow currents to form in power lines or interfere with satellite systems. Understanding how flares affect communication begins with the ionosphere, a region of Earth's atmosphere extending from about 60 kilometers to roughly 1,000 kilometers in altitude. Under typical conditions, the ionosphere has enough free electrons to reflect some radio frequencies back toward Earth, allowing communication over thousands of miles. This is the basic reason shortwave radio works, how aircraft crossing oceans maintain contact, and how ships communicate far from land. The ionosphere acts like a mirror for certain signals. When a flare releases X-ray and extreme ultraviolet radiation, the ionosphere becomes over-ionized. Instead of reflecting signals, it absorbs them. The mirror becomes a surface that soaks up radio energy. Australia experienced this exact effect. Aircraft, ships, and emergency services relying on high-frequency radio would have noticed the sudden loss. Nothing was broken. The atmosphere simply changed for a short period, and the signals could not travel. Now consider stronger events. An X 1.9 flare is moderate, the strongest flare of 2025 so far. The X 5.16 event on November 11th caused R3 blackouts across Africa and Europe. The strongest flare of solar cycle 25 so far was an X9 on October 3rd, 2024. Historical records show much larger events. The flare connected to the Carrington storm is estimated between X40 and X45, with some studies placing it higher. That is not 10 times stronger than the X 1.9 flare. It is not even 100 times stronger. It could be several hundred to 1,000 times more powerful. An X40 flare today would not only affect high-frequency radio communication, it could disturb GPS signals as they pass through a turbulent ionosphere. It could disrupt aviation, maritime transport, emergency services, banking systems that require precise timing, and power grids that depend on GPS-based synchronization. On the NOAA scale, an R5 extreme radio blackout describes complete high-frequency radio failure on the entire sunlit side of Earth, lasting several hours, accompanied by major navigation errors. That description is not speculation. It matches the expected effects of a Carrington-class flare. The Sun has produced such flares before. It will produce them again. The only unknowns are when the next one will occur and whether Earth will be aligned with it when it does. The event on December 1st served as a clear reminder that the Sun is active and capable of affecting the systems we rely on. It also showed how modern civilization has become dependent on technology that can be disturbed by a single well-aimed burst of energy from our star. The radio blackout that affected Australia lasted about 30 minutes and caused no lasting damage, but it came from a small region, while a much larger and more complex sunspot was still rotating into view. The next several days will determine whether active region 4294 will cross the solar disk without major incident, or whether it will release something far stronger than the X 1.9 flare that caused the Australian blackout. history suggests that staying calm does not mean ignoring the evidence. The Sun has displayed far more intense behavior in the past. In the year 1859, it released an event powerful enough to set telegraph equipment on fire. In 1989, it disturbed the magnetic field around Earth strongly enough to collapse an entire power grid, and long before written records, natural markers such as tree rings preserved signs of solar storms that exceeded even the Carrington Event. These older records show that the Sun has produced bursts of radiation strong enough to reach the ground and leave chemical traces in the wood of trees that lived through them. The Sun does not act with intent, but its activity has consequences. At times, the effects are quiet. At other times, they are forceful. The next significant period begins as the large sunspot moves into a position where its eruptions would be directed toward Earth. There is a specific window when the geometry between Earth and the Sun aligns in a way that increases the risk. For active region 4294, that window opens around December 4th and lasts until about December 7th. During this stretch of days, the region will travel across the central meridian of the solar disk, the area where any flare or coronal mass ejection would travel along a line that intersects Earth's orbit. Before and after this alignment, flares can still occur, but the ejector usually travels in directions that miss Earth. During the central window, any powerful release would be pointed toward our planet, with little room for error. This is why forecasters are paying close attention. NOAA's Space Weather Prediction Center has already issued their outlook for the first week of December. They estimate around a 70% chance of M-class flares and continued potential for additional X-class events through December 5th. A high-speed solar wind stream produced by a coronal hole is also expected to arrive around December 3rd, which may raise geomagnetic activity to gone storm levels. This particular coronal hole has influenced Earth before. In early November, it produced strong solar wind conditions, and now the same feature is returning. The official forecast uses careful language. It speaks in probabilities, not certainties. That tone reflects the nature of the science. Predicting solar behavior is challenging. Even so, the concern behind the wording is clear. Active region 4294 is not a typical sunspot. Its size, magnetic structure, and position during a period of elevated solar activity make it a region that requires close monitoring. Amateur astronomers have been studying and imaging the sunspot from many locations. An observer in Sedona, Arizona, captured the region as it emerged over the southeastern limb and noted that it appeared potentially hazardous. Another observer in France described the complex magnetic structure, noting bright areas and dark filaments that aligned with the magnetic field lines. These observations come from experienced individuals familiar with the patterns of solar behavior. They are not exaggerations. They reflect the early signs of a region carrying significant magnetic stress. The delta magnetic configuration remains the most important factor in these assessments. Magnetic polarity determines how stable or unstable a region is. A simple way to imagine this is by thinking of two bar magnets placed near each other. If opposite poles face each other, they attract and settle into a stable arrangement. If the same poles face each other, they repel and create tension. On the Sun, these magnetic polarities are embedded in plasma that rises and falls, moving in complex patterns. Their field lines twist and stretch under those motions. The energy stored in those twisted lines grows over time and eventually must release. Delta-class sunspots tend to release their energy in sudden outbursts rather than through slow, steady processes. More than 80% of major flares originate in regions with delta configurations. These areas are responsible for most of the X-class flares that affect satellites, communications, and sometimes power systems. Active region 4294 has shown signs of delta structure since it came into view. As it continues to rotate into a clearer position, more details become visible. NOAA has already divided the region into separate numbered groups because of its size and complexity. This is not a single sunspot. It is a large connected system of magnetic features that dominates a significant part of the northeastern solar quadrant. The behavior of solar cycle 25 adds more context. This cycle was expected to be mild, continuing the downward trend seen in cycle 24. When predictions were made in 2019, they estimated a maximum of around 115 sunspots occurring sometime in July of 2025. Those expectations did not match the actual behavior. The sun increased its activity sooner than expected. In October of 2024, the prediction panel acknowledged that the solar maximum had already begun, possibly as much as 2 years ahead of schedule, and that the intensity was stronger than earlier projections. This matters because solar maximum is the period when active regions are most likely to produce large eruptions. Not every major flare occurs in maximum, but the chances rise as the magnetic field grows more complex. We are currently in that stage, and the sun is displaying higher activity than expected. Into this environment comes the largest sunspot observed in about 10 years, moving toward its most geo-effective position. The next 72 hours form a critical period. This does not mean a major event is certain. Some large sunspot groups cross the disk quietly. They release only small flares, dispersing their energy slowly rather than explosively. Stability is possible, but the magnetic configuration of active region 4294 does not strongly suggest stability. The X-class flares from nearby areas also point to elevated activity, and the overall behavior of the current solar cycle suggests that expecting a completely quiet outcome may be unrealistic. Space weather forecasting involves a level of uncertainty that exceeds typical weather prediction on Earth. Meteorologists rely on dense networks of sensors and well-tested models. Space weather scientists depend on a smaller set of satellites and models that are still improving. The sun often behaves in ways that challenge assumptions. Forecasters can describe conditions and probabilities, but they cannot predict precise outcomes. They cannot say with confidence whether active region 4294 will generate an X10 flare tomorrow or weaken over the next week. The sun determines the timing. What scientists can do is prepare. Power grid operators have been notified of the increased risk. Satellite teams have received alerts. Airlines that fly near the poles, where communication is more vulnerable and radiation is stronger, have information to plan their routes. These steps are part of normal procedure during active periods. They happen several times each year. Sometimes the sun produces an event. Sometimes it does not. The preparations continue either way. Most people are unaware of this quiet, ongoing work. But there is a scenario that experts consider with concern. It is the scenario in which routine precautions are not enough, where an event exceeds the limits of what infrastructure was designed to handle. The Carrington Event was such a case, though it arrived in a world without modern electrical grids. A similar event today would interact with a sensitive, interconnected technological society. Communications, navigation, timing systems, satellites, and power grids depend on stability in the space environment. A major solar storm would challenge that dependence. We have spent more than 160 years expanding a system that is vulnerable to the kind of disturbance a large solar event can deliver. Many parts of that system were built without considering extreme solar risks. Hardening the infrastructure is possible, but it is a long and complex process. Solar storms will continue to occur whether or not humans are prepared for them. The next few days may pass without a major flare. The large sunspot may rotate harmlessly across the solar disk, Many sunspots have done exactly that, leaving behind only small disturbances and striking images for observers. This is the most common outcome. Most active regions do not produce catastrophic events, and most solar cycles do not include storms on the scale of the Carrington Event. The base rate of extreme solar storms is low, but low probability is not zero probability. And when the consequences of an event could be severe, even low probabilities deserve attention. Financial institutions describe such possibilities as tail risks, rare outcomes that can still cause major impacts. Space weather has similar risks. Active Region 4294 has placed the world in a moment of heightened awareness because the conditions for a significant event are present. The Sun has produced Carrington-level storms before. Natural records show this clearly. Historical accounts, though limited, support it, and the Sun will produce such storms again. The timing is the only unknown. It might happen this week, this year, this decade, or much later. The appearance of active region 4294 does not guarantee that this is the moment, but it signals that the probability is higher than usual and that the immediate period deserves close attention from everyone who relies on the technology that a strong solar storm could disturb. In today's world, that includes everyone. On the morning of September 1st in the year 1859, an English astronomer named Richard Carrington, 33 years old at the time, was carrying out his usual routine. On clear days, he projected an image of the Sun onto a white screen and drew the sunspots he observed. His observatory at Red Hill in Surrey was small but reliable. Using a 4.5-inch telescope, he had tracked solar features with care for many years. His observations contributed to the growing scientific effort to understand the Sun in a more systematic way. That morning, he saw a large cluster of sunspots in the northern hemisphere of the solar disk. The group looked active and complex, with shapes that suggested magnetic tension. As he continued sketching, something happened that had never been described in scientific literature. At 11:18 local time, two bright patches of white light appeared inside the sunspot group. They were brilliant enough to stand out against the bright solar surface. Carrington watched as the bright areas shifted across the sunspot, covering a distance of about 35,000 miles in roughly 5 minutes before disappearing. He had witnessed what is now known as a solar flare. Although he did not yet have the words or framework to identify it, Carrington tried to find another person to confirm the sighting, but the event ended before he could bring anyone to witness it. Unknown to him, another astronomer, Richard Hodgson, observing from a different location in London, saw the same phenomenon. Their detailed accounts later appeared in the monthly notices of the Royal Astronomical Society, becoming the first published observation of a white light flare. What followed the flare was unlike anything recorded in human experience up to that point. About 17.5 hours after the flare, Earth was struck by a geomagnetic storm of extreme intensity. The speed was remarkable. Coronal mass ejections normally take between 2 and 4 days to travel from the Sun to Earth. The one associated with the Carrington event arrived in under 18 hours. This suggested either extreme velocity or that an earlier ejection had cleared the solar wind path, allowing the later ejection to move with unusually low resistance. The effects were immediate and global. Telegraph systems across Europe and North America malfunctioned. Operators reported strong electrical shocks when touching their equipment. Telegraph paper ignited in several offices. In some cases, the currents induced by the storm were so strong that telegraph operators disconnected their batteries entirely and continued sending messages using only the electricity produced by the geomagnetic disturbance. At the same time, the aurora reached latitudes far beyond its usual boundaries. The northern lights were seen as far south as the Caribbean, as far west as Hawaii, and as far south as Colombia. In the Rocky Mountains, miners woke before dawn, believing daylight had arrived because the auroral glow was so bright. Across the world, people saw the sky illuminated in red and green colors they had never witnessed before. The Carrington Event became known as the most intense geomagnetic storm ever documented. Estimates of its strength suggest it was roughly twice as powerful as the next largest measured event. The disturbance index, which measures geomagnetic intensity, is estimated to have reached between 800 and 1,750 nanotesla. By comparison, the March 1989 storm that caused the collapse of the Quebec power grid peaked at about 589 nanotesla. The Carrington Event was 2 to 3 times stronger than the storm that disabled a significant portion of Canada's electrical infrastructure. But in 1859, the world had very little that could be damaged. Daily life ran on steam engines, animal power, and open flame. The telegraph was the only electrical system widely used, and even it had not reached much of the world. There were no power grids, no satellites, no global navigation systems, and no internet. The Carrington Event caused local damage and widespread surprise, but not a crisis. The conditions that would have made such an event dangerous simply did not exist. In the century and a half since then, society has built exactly the systems that such an event could harm. Electricity is now the foundation of nearly everything people depend on. Without power, water treatment plants stop functioning. Pumps that deliver clean water to homes stop running. Wastewater systems dependent on powered lifts begin to fail. Hospitals lose the ability to use ventilators, dialysis machines, and temperature-controlled medication storage. Gas stations cannot pump fuel. Grocery stores lose refrigeration and digital payment systems. Traffic lights shut down. Communication networks fail after cell towers deplete their backup batteries. Within hours of a major outage, secondary effects accumulate. Within days, the situation becomes a serious emergency. Within weeks, it can threaten large populations. A storm on the scale of the Carrington Event would not be a minor disruption for the modern world. Researchers have tried to estimate the potential cost. Lloyd's of London commissioned a study in 2013 to analyze the effects of a Carrington-class storm striking the United States. Their estimates ranged from $600 billion to $2.6 trillion depending on severity and duration. Adjusted for inflation, those numbers would be even higher today, and the study largely considered only direct damage. It did not fully account for cascading failures that would follow prolonged power outages across several states. The central vulnerability lies in the high-voltage transformers that support the grid. These devices can weigh more than 400 tons and are needed to step voltage up for long-distance transmission and down for local distribution. They are costly, take 12 to 18 months to build under normal conditions, and are typically custom manufactured overseas. The United States has around 2,000 such transformers. There is no large reserve of spares. If even a small portion of them were damaged, parts of the grid could remain without power, not for hours or days, but for months or possibly years. The mechanism of damage is straightforward. When a coronal mass ejection compresses Earth's magnetosphere, it induces electric currents in long conductors, such as power lines. These geomagnetically induced currents travel through transformers. Transformers are built for alternating current, not the quasi-direct current generated during geomagnetic disturbances. The induced current forces the transformer core into saturation, generating heat in areas not designed to withstand it. Insulation breaks down. Hotspots form, and in severe cases, windings can melt. Fires are also possible. This is not theoretical. During the March 1989 storm, which had only 1/3 the estimated intensity of the Carrington Event, the Hydro-Quebec grid collapsed. in 92 seconds. 6 million people lost power in the middle of winter. A transformer at the Salem Nuclear Station in New Jersey failed due to induced currents. In the following 2 years, 11 nuclear plants reported failures in generator step-up transformers, likely related to the storm. And yet, that storm was not close to Carrington's strength. The European Space Agency conducted simulations in 2025 to examine how a Carrington-level event would affect satellites and infrastructure. Their findings showed possible atmospheric expansion up to 400%, which would increase drag on satellites and alter orbits. Communication blackouts and GPS disruption were likely. Tracking space debris would become more difficult as atmospheric density increased. The exercises showed how unprepared we remain for an event that has occurred before and will occur again. Carrington suspected that the bright flare he saw was linked to the geomagnetic storm, but he noted that one observation was not enough to prove the connection. Today, the physics is well understood. Solar flares release electromagnetic radiation that arrives at Earth in minutes, disturbing the ionosphere. Coronal mass ejections follow hours or days later, interacting with the magnetosphere and causing geomagnetic storms. The connection is not theoretical. It is measured continuously by spacecraft and ground stations. What has not happened is a large-scale effort to harden infrastructure against such events. High-voltage transformers remain susceptible. Spare component stockpiles remain inadequate. Warning systems can provide some notice, but grid hardening requires years of work, not hours or days. Operators can reduce load or isolate equipment, but they cannot fully protect a fragile system from a major solar storm with last-minute measures. The Carrington Event was a warning written in the sky of 1859. The people of the time marveled at it, documented it, and then built a technological society without remembering the lesson it offered. The sun has not changed. It remains capable of releasing massive storms and sending magnetized plasma into space at thousands of kilometers per second. The only change is our increasing dependence on systems vulnerable to these events. The question is not whether another Carrington-level storm will occur. It will. The question is whether we will be prepared when it happens. At present, the answer is almost certainly no. Whispers in the tree rings. In the tree rings, the story does not end with the Carrington Event. It continues into more distant centuries, where another kind of evidence waited to be found. In 2012, a physics graduate student at Nagoya University in Japan made a discovery that quietly changed how scientists think about extreme solar activity. Her name was Fusa Miyake. She was not searching for anything dramatic. Her project focused on improving a very sensitive method for measuring carbon-14 in tree rings. This was an advance in radiocarbon dating that allowed her to study individual annual growth rings instead of averaging samples over many decades. To carry out this work, she traveled to a green island in southern Japan, known for its ancient cedar trees. Some of these trees were nearly 1,900 years old. She took a slice from an old stump, counted the rings one by one back through the centuries, and began measuring the radioactive carbon levels year by year. When she reached the ring that formed between the years 774 and 775 AD, she found something that did not fit any normal pattern. The amount of carbon-14 in that ring was about 12% higher than in the neighboring rings. This was not a slow rise. It was not a small error in measurement. It was a sharp jump confined to a single year. The change was roughly 20 times larger than the usual year-to-year variation caused by normal cosmic radiation. Something had happened in the year 774 or 775 that caused a sudden and intense increase in the production of carbon-14 in Earth's atmosphere. It was brief, powerful, and global, and its trace had been quietly stored in the wood of trees for more than 1,000 years. Carbon-14 forms when high-energy particles from space strike nitrogen atoms in the upper atmosphere. These collisions knock out protons and convert the nitrogen into a radioactive form of carbon. That carbon-14 then joins with oxygen to form carbon dioxide. This carbon dioxide mixes through the air and is absorbed by living organisms. When a tree grows a new ring during a given year, it uses the carbon dioxide available at that time, including whatever carbon-14 is present. Once that ring is complete, the carbon inside it is effectively sealed in place. Over thousands of years, the carbon-14 decays at a known rate. By measuring how much remains, scientists can determine when the ring was formed. Miyake was not trying to determine the age of the tree. She was trying to map changes in cosmic ray intensity over time. The spike in 774 told her that the flux of high-energy particles reaching Earth had temporarily increased by a very large amount. Other research groups soon checked her result. They found the same sudden rise in carbon-14 in tree rings from Germany, Russia, the United States, Finland, and New Zealand. Whatever caused the event, it affected the entire globe. A matching spike in beryllium-10, another isotope created by cosmic rays, was later identified in Antarctic ice cores from the same period. Taken together, the tree ring data and the ice core data showed that Earth had been hit by an intense burst of high-energy particles around 774 or 775 AD. The most straightforward explanation was that the source had been the Sun. During solar flares and coronal mass ejections, the Sun can accelerate particles to high energies and send them toward Earth. Those particles can interact with the atmosphere to produce carbon-14 and beryllium-10 in exactly the way Miyake's data showed. But the magnitude of the spike created a problem. The Carrington Event, the largest solar storm in the written record, did not leave a clear mark in the cosmogenic isotope record. It was too small. The 774 event had to be at least 10 times stronger than the Carrington storm, and some estimates suggested it might have been 80 times stronger. It appeared that the Sun had produced a storm far more powerful than anything humanity had ever observed directly. These extreme events are now called Miyake events, named after the graduate student who first recognized their signal in tree rings. After the 774 discovery, scientists began looking for similar patterns in other time periods. They found another spike centered on 993 to 994, a D about 60% as strong as the 774 event. Additional events were identified around 660 BC, 5259 BC, 5410 BC, and 7176 BC. The strongest known event occurred roughly 14,300 years ago. Its trace was found in very old trees, preserved in riverbanks in the French Alps. That event appears to have been about twice as strong as the 774 spike, which itself was already an order of magnitude above anything seen in the historical record. The implications are large and clear. These events are not hypothetical. They happened. The evidence is preserved in ancient wood and ancient ice, natural archives that do not exaggerate and do not have opinions. They simply record what passed through the atmosphere in the years when those rings and layers formed. The Sun has produced storms of extraordinary intensity several times during the Holocene, the geological epoch that covers all of human civilization. These storms did not wipe out life. They did not stop history. Empires rose and fell for their own reasons. But the storms did occur before humans built a technology-dependent society vulnerable to the effects of such radiation. To understand what a Miyake event might mean for the present, it helps to imagine one happening today. This would not be a Carrington-scale storm. which is already considered an extreme case in most planning. It would be something tens of times more powerful. A Carrington-level storm could overload power grids and damage transformers. A Miyake-level event could go much further, at high flight altitudes, especially along polar routes where Earth's magnetic shield is weaker. The radiation dose could become dangerous or even life-threatening for passengers and crew. Satellites would be struck by particle fluxes strong enough to damage or destroy their electronics outright, not through slow wear, but through immediate failures in circuits and components. The ionosphere would be disturbed so severely that global navigation systems might be unreliable or unusable for days. Signals from GPS satellites could be bent, delayed, or blocked in ways that receivers are not designed to handle. Power grids would be exposed to induced currents well beyond their design limits. The resulting failures would be faster and more widespread than in current worst-case models. Recovery could take much longer, especially if many key components failed at once. Historical written records from the time of the 774 event offer only faint clues. The Anglo-Saxon Chronicle, a collection of early English historical notes, includes an entry describing a red cross in the sky seen after sunset in the year 774. This matches what might be expected from an intense aurora, visible at unusually low latitudes. Chinese records from the same period mention unusual lights in the sky, but the descriptions are brief. The people who saw these displays had no concept of solar particles or atmospheric chemistry. They interpreted the lights as signs or omens, not as physical events that could be measured and modeled. Modern science can now read those same events through a different lens. By combining ancient writings with isotope records, researchers can say with confidence that Miyake events are real. They seem to occur on timescales of many centuries to about 1,000 years, and they represent a level of solar activity far beyond the strongest storms in written history. The rough rate appears to be around 1 event per 1,000 years, although the statistics are uncertain because the number of identified events is still small. 1,000 years is a long time for a human life, but brief in terms of geology or solar evolution. The last confirmed Miyake event happened in 993 or 994 AD, a little more than 1,000 years ago. From a statistical point of view, we are now in a period where another such event is not unlikely. There is still an active debate over whether all Miyake events are caused by the sun. The energy required is high, and some solar models struggle to produce such large outputs without adjustments. Some scientists have suggested that at least some of these spikes might have been caused by other sources, such as nearby supernovae or gamma-ray bursts. However, the evidence at present leans toward a solar origin. The isotope patterns match what is expected from solar energetic particles rather than from distant cosmic explosions. The timing and duration also seem more consistent with extended solar activity than with a brief external flash. The sun has already shown that it can surprise us. It may simply be that we have not yet fully mapped the most extreme edges of its behavior. The fact that the mechanism is not fully understood adds another layer of concern. We do not know exactly how the sun generates Miyake events. We cannot yet predict when the next one will occur. We only recognize their existence in the last decade thanks to careful measurements of carbon-14 in tree rings. Our knowledge is recent and incomplete. At the same time, we have built a civilization that would be deeply affected by such an event. Many of our critical systems assume a certain range of space weather conditions. A Miyake event would push well beyond those assumptions. The tree rings quietly carry a message across time. They tell us that the Carrington event, while serious in our planning, is not the upper limit. They show that the sun has, on several occasions, released storms far more powerful than anything we have recorded with telescopes and satellites. They remind us that we are living under a star capable of levels of activity that we have never personally seen. As a result, we are making a kind of bet. We are assuming that these extreme events are rare enough that one will not occur during the lifetime of our current infrastructure. The odds in any one year are low. That makes the bet feel safe. But the risk does not vanish. It simply stretches across time. The consequences of losing that bet would be severe. The ancient cedars of Japan have been adding rings for nearly 2,000 years. They recorded the 774 event and the 994 event without knowing what they were capturing. They continue to grow today, building new layers that record the cosmic ray environment year by year. Somewhere in those outer rings, the story of the current solar cycle is being written. Future scientists will be able to examine those rings and see how active the Sun was in 2025, how many particles reached the atmosphere, and whether anything unusual took place during the time when the largest sunspot in a decade rotated into view. From our position now, we cannot see what they will find. We can only monitor the Sun as best we can, strengthen what we are able to strengthen, and recognize that our picture of solar extremes is still incomplete. The tree rings broaden the range of what we know is possible. They suggest that the safe limits we have assumed for our technology may not match the true limits of solar behavior. Whether the Sun will test those limits while our systems are in place is a question only time can resolve. The first 48 hours of darkness. Imagine a major solar storm not as a distant possibility but as a concrete event unfolding in real time, affecting ordinary people in their daily lives. A massive coronal mass ejection bursts from a complex sunspot region and is directed straight toward Earth. Forecasters detect the eruption immediately. Images from coronagraph instruments show a complete halo of expanding material around the Sun, a sign that the ejected plasma is moving directly along the line between the Sun and our planet. Early velocity readings confirm what no one wanted to hear. This coronal mass ejection is traveling at more than 2,000 kilometers per second. At that speed, it will reach Earth in less than 18 hours. Warnings go out to operators of power grids, satellite companies, airlines, and government agencies. Public announcements advise people to expect possible disruptions. Most people hear the news, note it briefly, and return to their normal routines. Geomagnetic storms happen from time to time. Lights flickered a bit during the one in May. Nothing seemed dangerous then. Many assume this will be the same, but the storm arrives ahead of schedule. It strikes Earth's magnetosphere in the early morning hours. The magnetic field carried by the ejected plasma is oriented southward, the most unfavorable direction. A southward field allows the solar material to link efficiently with Earth's magnetic field, transferring energy into the magnetosphere. The magnetic shield compresses sharply. Electric currents begin flowing through long conductors at the surface, including power lines, pipelines, and large communication cables. Within minutes, the first transformers start to overheat. Operators who had already begun precautionary procedures watch their equipment destabilize faster than they can respond. High voltage breakers trip. Load distribution becomes unstable across multiple regions. At the same time, voltage conditions fall out of balance, and the interconnected sections of the grid begin to influence one another in unpredictable ways. Entire networks shut down. The lights go out. In the first hour, the situation feels familiar to people in affected areas. It seems like a standard blackout, the kind that happens during storms or severe weather. People reach for their phones to find out what happened. Many cannot load websites because the local networks are overwhelmed. Cell towers have backup batteries, but increased demand slows the system. Some people manage to read early reports. The outage is not limited to their city. Some states are dark. Other areas are reporting partial service. The full scale of the event remains unclear. By the second hour, traffic has turned chaotic. At intersections without traffic lights, Drivers are supposed to treat the crossing as a four-way stop. Many people do not. Collisions begin to block major roads. Emergency services hurry from one incident to another, but their communication networks are strained. Some systems are degraded by partial interference from the storm. Others are congested from the sudden spike in demand as people call for help. Hospitals switch to backup generators. They begin to notice that some sensitive equipment is malfunctioning. Diagnostic machines give inconsistent readings. Monitoring devices reset unexpectedly. Staff improvise, switching to older manual techniques. By the fourth hour, daylight reveals a landscape that has changed overnight. Regions untouched by the storm continue as normal, but they are fewer than expected. Utility companies attempt to map the extent of the damage. Several states have lost all power. Others have limited service in isolated pockets. Grid operators work to isolate damaged lines and restore service where possible. But progress is slow. Financial markets do not open. Systems that depend on precise timing from global navigation satellites are malfunctioning. Those satellites are still transmitting, but their signals are distorted by ionospheric turbulence. Trucking companies lose accurate tracking of their fleets. Airlines halt flights because navigation systems are unreliable and communication channels remain degraded. For many households, the fourth hour brings the first practical inconveniences. Refrigerators are warming. Food begins to soften. Gas stoves still work for some, but electric stoves and microwaves are silent. Water continues to flow because elevated storage tanks maintain pressure through gravity. The pumps that refill those tanks, however, remain offline. Few people worry yet. The outage is still fresh. It seems reasonable to expect restoration soon. By the 12th hour, that expectation weakens. Cell phone batteries are failing. Without a way to recharge them, information becomes scarce. Rumors spread. Some believe the entire nation is without power. Others think the grid will be restored by evening. Reliable updates are difficult to find. The internet is mostly inaccessible. Television is unavailable. Even battery-powered radios struggle to find stations still broadcasting. The first night without power feels unsettling. Cities that normally glow with artificial light become dark and quiet. Stars appear in places where light pollution usually hides them. The sight is unusual, but does not comfort people for long. Homes in cold areas lose heat. Homes in hot areas lose air conditioning. People add layers of clothing or adjust windows to keep rooms livable. Most still believe the outage will end soon. By the 24th hour, water pressure fades in some neighborhoods. The elevated tanks are emptying, and the pumps remain offline. Faucets slow to a trickle, and then stop. People begin to recognize that water is essential, and that the situation may be more serious than they assumed. Grocery stores, operating with cash and manual records because electronic payment systems are down, run out of bottled water as demand rises sharply. Supplies that would have lasted days under normal conditions vanish within hours. By the 36th hour, fuel shortages begin. Gas stations cannot pump gasoline without electricity. Some stations have generators, but the generators require diesel, and the supply is limited. Trucks transporting goods cannot refuel. Many cannot operate efficiently without accurate GPS tracking. Roads are cluttered with stalled vehicles. The supply chain, a delicate network that keeps shelves stocked and deliveries on schedule, begins to fail. Perishable foods spoil in warehouses. Refrigerated trucks become warm storage containers. By the 48th hour, the scale of the crisis becomes clearer. This is no longer a standard outage that can be fixed by repairing a few lines. Transformers have been damaged beyond simple repair. Their windings are burned. Their internal oil is contaminated. Their cores have been magnetically saturated in ways that cannot be reversed. These units must be replaced. Some replacements do not exist. Others take 18 to 24 months to manufacture, even under normal conditions. When demand surges suddenly, timelines grow even longer. Grid operators do what they can. They attempt to restore power to critical infrastructure first. Hospitals, water treatment plants, and emergency services receive the initial focus, but the available generating capacity has been sharply reduced. Transmission lines that survived the storm still depend on transformers that no longer function. 48 hours without electricity is manageable for most people. It is uncomfortable and stressful, but not deadly. The greater danger lies in what happens afterward. If power returns within a week, the region can recover, losses will be counted, repairs will be made, and life will slowly return to normal. But if the outage lasts weeks or months, basic systems begin to fail in ways that threaten lives. Food shortages worsen. Water scarcity becomes critical. Medical conditions requiring powered equipment become emergencies. The social structure, already strained, begins to show signs of deeper stress. This scenario is not fictional. It appears in multiple government and industry assessments. The Federal Energy Regulatory Commission has identified 30 critical high-voltage transformers whose failure could cascade into a nationwide blackout. Some studies suggest that losing as few as 9 key transformers in specific locations could produce a coast-to-coast outage. Recovery from such an event would take months or even years, depending on how many components were damaged, how many replacements were available, and how much secondary harm occurred during the outage. In the first 48 hours, most people would have no clear understanding of the long-term consequences. They would ration their remaining phone battery power, eat what they have stored, and assume that assistance was on the way. They would expect normal life to return. That expectation would fade later on the 3rd day, the 4th day, or sometime during the first week without power. Once supplies run out and aid does not arrive, the nature of the situation changes. What began as an inconvenience becomes a crisis. The crisis tests the resilience of communities in a way that has not been required since the development of the modern electrical grid. All of this can begin with one solar storm, one burst of magnetized plasma that we can detect in advance but cannot stop. The warning may be 18 hours. It may be less. Preparations made within that window have limits. When the storm reaches Earth and geomagnetically induced currents begin to flow, the outcome depends entirely on choices made long before the event. It depends on whether the grid was reinforced, whether spare equipment was stored, whether systems were designed with the full range of solar activity in mind. 48 hours without power is only the beginning. When water stops flowing, the order of basic needs becomes clear, and the systems people rely on every day start to reveal how fragile they truly are. Electricity is the foundation that supports modern life. It powers the pumps, the sensors, the control systems, and the treatment facilities that make clean water possible. But electricity itself is not what keeps people alive. Water does. Clean, safe, pressurized water delivered into homes and buildings, available at any time with the turn of a handle. People drink it, cook with it, bathe with it, and use it to remove waste from their homes. In the United States, the average person uses between 80 and 100 gallons per day. Most of that use happens without conscious thought, and almost all of it depends on electricity. Water treatment facilities operate continuously. They take raw water from reservoirs or rivers and pass it through filtration, sedimentation, and chemical treatment. After treatment, they pump the water into distribution systems. The pumps that draw water from reservoirs need electricity. The pumps that send treated water into elevated storage tanks need electricity. The sensors that monitor water quality, the chlorine injection systems that prevent disease, and the computers that regulate pressure across the network all require a steady supply of power. When that power disappears, the entire system begins to break down. Most cities maintain some reserve capacity. Elevated tanks store water above the distribution system so that gravity can maintain pressure even when pumps stop running. Some states have specific requirements. For example, regulations in Texas require large cities to store at least 200 gallons per connection, with half of that amount in elevated or pressurized tanks that can operate without power. Other states have similar standards. These reserves provide a buffer that can last from several hours to a couple of days depending on local consumption. But a buffer is only a delay. It does not solve the underlying problem. Every gallon that flows from a faucet during an outage is a gallon that cannot be replaced until the pumps are running again. Once the elevated tanks empty, the pressure drops, taps sputter, and the flow stops entirely. In most urban areas, 2 to 3 days of grid failure is enough to exhaust gravity-fed storage. After that point, water does not move without electricity. When the supply stops, consequences appear quickly. Hospitals rely on water for sterilizing equipment, cooling certain machines, maintaining basic sanitation, and supporting patient care. Even hospitals with backup generators face serious challenges once their water supply disappears. Fire departments rely on hydrants that draw from the same system. When pressure fades, hydrants produce only a weak flow. A house fire that would normally be contained becomes uncontrollable. A building fire becomes a major threat. Sanitation systems also depend on flowing water. Toilets back up. Sewage lines clog. Homes become unpleasant within days, and the odor spreads across neighborhoods. When sanitation fails, the risk of disease increases. In parts of the world where water systems collapse, outbreaks of cholera, typhoid, and dysentery often follow. In developed countries, these diseases are less common, but the conditions that support them can form quickly when clean water is unavailable. Contaminated sources, poor hygiene, and crowded populations searching for resources create an environment where illness can spread. Public health systems that would normally respond are limited by the same outage. Laboratories lack power, hospitals struggle with overcrowding, and communication networks do not function reliably. The psychological impact of losing water is significant. People can tolerate darkness for a while. They can tolerate heat or cold for a time. They can adapt to limited communication, limited transportation, and limited comfort. But the sudden absence of water creates fear. Water is essential to life, and the human body can last only a few days without it. When taps run dry, the sense of security that people rely on begins to erode. Even those who would never consider taking from others under normal conditions may change their behavior when their families face dehydration. Emergency water distribution in localized disasters is difficult but possible. When a hurricane or earthquake affects one region, other regions send help. Bottled water arrives by truck. Tankers refill local storage. People line up at distribution centers. But a nationwide grid failure affects all regions at the same time. There is no unaffected area to supply aid. National Guard units that would normally deploy to help other states are needed at home. Federal agencies face shortages of personnel and transportation. The scale of the need exceeds any existing contingency plan. The numbers illustrate the challenge. A single person needs about 1 gallon of water per day for drinking and minimal hygiene. A family of 4 needs 4 gallons. A city of 1 million people requires 1 million gallons per day just for drinking, with no allowance for cooking, sanitation, or medical use. That 1 million gallons is equal to about 3,800 tons of water. Moving that amount by truck when fuel is scarce, roads are congested, and navigation systems are unreliable is nearly impossible. Supplying water to a national population of more than 330 million people under those conditions is far beyond any realistic capacity. When municipal water fails, natural sources become the only alternative. Rivers, lakes, streams, and wells provide water, but they are not necessarily safe. Surface water often contains bacteria, parasites, or chemical contaminants. Drinking untreated water can cause illness or death. Rural communities with wells and manual pumps have better chances. Urban and suburban areas are at greater risk. People may drink from any available source out of desperation, and many will become sick. Purifying water is not a simple task for those who have never done it. Boiling water works, but it requires fuel. Filtration systems and chemical treatments can help, but they are not widely available in large urban areas. Many households have no equipment or knowledge for water purification. Fuel shortages make boiling difficult. Natural gas systems may fail, and many homes use electric stoves. Wood can be burned, but wood is scarce in dense cities. The number of people who can successfully purify enough water for their families is small. The timeline of dehydration is unyielding. A healthy adult may survive 3 to 5 days without water depending on activity level and climate. Children and older adults are more vulnerable. Those with medical conditions may require more frequent hydration. By the 4th or 5th day of a widespread outage, if water has not been restored or replaced, deaths begin. They come first from dehydration, not from violence or infection. This progression is predictable and documented in multiple studies. Water infrastructure is classified as critical because of this direct connection to survival. Utilities prioritize water systems when deciding how to use emergency power. Plans exist for limited disruptions, but these plans assume that electricity will return within hours or days. They do not account for a nationwide grid failure that lasts weeks or months. The events of 1989 in Quebec offer one data point. Power was restored in 9 hours, and water systems remained functional. The blackout of 2003, the largest in North American history, lasted roughly 2 days for most people. Water continued to flow. These events show that brief outages are manageable. What they do not show is how the system behaves under prolonged failure at national scale. No modern society has experienced that scenario. Studies that model such conditions reach similar conclusions. The primary cause of mass casualties would not be fire, cold, or even loss of medical care. It would be the failure of water and sanitation systems. A congressional commission studying the effects of electromagnetic disturbances estimated that a prolonged nationwide outage could lead to the death of between 2/3 and 90% of the United States population within 1 year. That estimate is controversial and considered by some to be extreme. But even conservative assessments acknowledge that millions could die if water systems fail for an extended period. The sun does not act with intent. It is a sphere of plasma undergoing nuclear fusion. Solar eruptions are natural processes, not directed attacks. But the consequences of those eruptions fall on a society built on assumptions of stability. People assume that water will always come from the tap and electricity will always be available. They live in cities that cannot support human life without constant technological support. These assumptions hold under normal conditions. The grid is durable, water systems have redundancies, emergency plans exist. But past solar events show that the sun can exceed the limits those plans were built to handle. When water stops flowing, the countdown begins. 3 days, perhaps 5. After that, survival depends on finding alternatives. The essential question is not whether water systems can fail. They can. The question is whether enough preparation has been made to prevent that failure, or whether society is relying on luck to avoid an outcome that is both understood and foreseeable. Modern civilization functions like a giant machine built from countless parts working together across long distances. Most people never notice this because they live inside it. Food appears on shelves every morning, coming from farms and factories hundreds or thousands of miles away. Fuel arrives at gas stations without anyone thinking about the refineries, pipelines, tankers, and storage terminals that keep the system moving. Medications come from complex global supply chains involving chemical plants, transportation networks, and computerized inventory systems. None of these flows remain steady by chance. They stay steady because electricity, communication networks, and digital tools keep every step coordinated. When the power disappears, this machine does not slow down gently. It stops sharply, and the failure spreads from one system to the next. The supply chain that feeds millions of people is designed for speed and efficiency, not for shocks. Warehouses don't hold weeks of food because software lets stores restock quickly. Manufacturers avoid keeping large reserves because just-in-time delivery saves money. These practices reduce waste and cost, but they also remove safety margins. A long power outage breaks many links at once. Trucks cannot move without fuel. Gas stations cannot pump without electricity. Drivers cannot plan routes without communication or GPS. Warehouses cannot process orders. Payment systems go offline. The simple act of moving a shipment from one place to another becomes nearly impossible. Stores empty out not because food has vanished, but because the systems that move it have stopped functioning. Fuel quickly becomes the most important bottleneck. Every part of society depends on it. Transportation, emergency services, generators, shipping, and agriculture all rely on a constant supply. Refineries need electricity to operate. Pipelines need power to push fuel long distances. And storage facilities depend on monitoring systems that also require electricity. Even if the Strategic Petroleum Reserve contains millions of barrels, the fuel is useless if it cannot be transported. Once deliveries fail, backup generators at hospitals and other critical sites begin to run out of fuel as well. When they stop, the last safety layer disappears. As the outage grows longer, communication fades. Cell towers run on batteries for a while. But when those drain and diesel backups run out, the network shuts down. Internet service disappears entirely. Radio stations may stay on briefly if their facilities have power, but many will go silent as generators empty. People lose the ability to reach relatives, check news, or receive official instructions. Without communication, confusion grows. Many communities realize they are facing the same challenges with no outside support on the way. Food quickly shifts from an everyday necessity to a source of stress. Most households keep only a few days of supplies. In an extended emergency, that stock disappears quickly. Food banks cannot resupply. FEMA's emergency meal reserves are far too small for a national crisis and cannot reach people if transportation is offline. Even well-prepared families face rising pressure as days stretch into weeks. The military, often assumed to be the fallback resource, depends on the same power and fuel systems as everyone else. It cannot fully replace a failed national grid. Social order begins to strain as the situation worsens. At first, people share resources and support neighbors. Communities often show surprising strength in a short crisis. But as weeks pass, cooperation becomes harder when supplies dwindle. People who still have resources may feel threatened. Others may decide they must take what they need to survive. This shift has been seen in many parts of the world during major disasters or political breakdowns. Laws and norms hold as long as enforcement exists. When police communications fail, courts close, and detention centers cannot operate, formal enforcement weakens. the burden shifts to informal community standards and personal ethics. Many people follow them, but not everyone will. The broader economic effects reach far beyond the blackout zone. Stock markets would crash or remain closed. Financial institutions depend on precise timing systems that fail when GPS signals degrade or disappear. Without reliable data, international trade slows or halts. Factories in other countries relying on American markets or materials would shut down. Ships divert or remain idle. The impact spreads through global supply networks that rely heavily on U.S. infrastructure. Even if power returns after weeks or months, the recovery begins from a far lower starting point than before the storm. Companies disappear, banks face losses, and entire industries may need rebuilding. Insurance models attempt to estimate losses, but these models often assume a functioning society capable of long-term recovery. Lloyd's of London once estimated trillions of dollars in damage from a Carrington-level event, but that figure assumes that insurance companies survive, governments remain stable, and economic value still exists in recognizable form. In a severe enough disruption, the idea of insurance loses meaning because there is no system left to administer it. Some groups are especially vulnerable. Urban populations living far from local food sources struggle first. People who depend on refrigerated medications, powered medical devices, or regular treatments face life-threatening challenges within days. Those without transportation or financial resources have limited options. Children, the elderly, and individuals with chronic health conditions face the greatest risks. The impact is not evenly distributed. It reflects economic, geographic, and medical differences that already exist. Historical events provide warnings. After Hurricane Maria, Puerto Rico went months without full power, and the eventual death count reached thousands. The 2021 Texas freeze, lasting only a few days, caused hundreds of deaths. These events were regional and limited in duration. A national, months-long power failure would be far more severe. It would challenge every assumption that supports daily life. Heating, refrigeration, medical care, transportation, communication, and safety. A future historian might look back and note that the risk was well known. Reports from agencies, scientific studies, and industry assessments all pointed to the same vulnerabilities. Yet investments in grid protection, transformer reserves, and emergency planning remained limited. Decisions often favored short-term savings over long-term resilience. We optimized for efficiency, trusting that rare events would stay rare, and that the next major solar storm would occur in some distant future. The sun, of course, does not shape its activity around human expectations. It follows the physics of magnetic fields and plasma flows. When it releases a major burst, it does so without regard for the systems built on a small planet 93 million miles away. Future storms will arrive in their own time. When they do, they will strike whatever version of society exists at that moment, strong or fragile, prepared or unprepared. The collapse of modern systems would not happen slowly. It would unfold rapidly because the technologies we depend on are not designed to fail gently. They work extremely well under normal conditions, but do not handle extreme disruptions. The machine of civilization can run at remarkable speed, but it does not idle smoothly. When power stops, the hidden gears inside it grind to a halt, and the consequences cascade outward. Many ancient civilizations disappeared after periods of stress. Their declines were caused by drought, resource exhaustion, war, or internal conflict. Their ruins show what happens when the systems that support daily life can no longer function. Today's world is very different. but the lesson remains the same. Societies endure only as long as the structures they rely on continue working. When those structures fail on a large scale, recovery becomes uncertain. Whether a future solar storm triggers such a moment depends on choices made long before the event occurs. Investments in grid protection, transformer reserves, communication resilience, and emergency planning determine how well society withstands a major space weather event. If these choices are delayed or overlooked, the next powerful storm could reveal weaknesses that have been ignored for too long. A moment like this invites us to look back at the long arc of human history and ask what earlier societies discovered too late. We often assume our civilization is permanent, the natural endpoint of progress, and something that will keep moving forward with only improvements. That assumption appears safe because most people alive today have never seen widespread collapse. But history shows how easily this confidence can turn into a blind spot. Many earlier societies believed they were stable and destined to endure. Their ruins now tell a different story. The Maya built cities that once held hundreds of thousands of people. They developed detailed mathematics, tracked celestial movements with impressive accuracy, created written texts, and built large stone complexes that still stand today. Their descendants remain in Central America, but the civilization that built Tikal and Chichen Itza entered a long decline between 800 AD and 1000 AD. Populations in some regions dropped by 90% or more. Urban centers were abandoned, and once thriving cities were overtaken by the surrounding forest. A society that had lasted more than 1,000 years could no longer maintain itself. Researchers continue to debate exactly why this happened. The likely explanation involves several stresses occurring together, including drought, environmental strain from deforestation, increased conflict, and political fragmentation. But at the core was a simple reality. The Maya created systems that supported large populations as long as conditions remained within certain limits. When those limits were exceeded, the systems failed, and the population could not be sustained at its earlier scale. Once the network weakened, decline unfolded over years and decades. The Bronze Age collapse around 1200 BC was even more abrupt. Across the Eastern Mediterranean, nearly every major society fell apart within about 50 years. The Hittite Empire vanished entirely. The Mycenaean kingdoms in Greece collapsed and entered a period often called a Dark Age that lasted roughly 4 centuries. Egypt survived but was permanently weakened. Historical texts speak of the Sea Peoples, a group or groups that attacked multiple regions. Yet, they were likely only one part of a much larger pattern. Drought, famine, earthquakes, internal revolts, and disease may all have played roles. What made the collapse dramatic was how interconnected the region had become. Trade, diplomacy, and shared technologies had tied these societies together. When stresses rose, the failures reinforced one another. The common theme in these examples is complexity. Complex societies offer many advantages. They support larger populations, create advanced technologies, and produce higher levels of wealth. But complexity requires constant energy and coordination. It also increases interdependence. When everything works, this system can achieve remarkable results. When part of the system fails, the effects spread quickly. Specialized knowledge also becomes concentrated in certain groups or institutions. If those institutions fail, or if the specialists are lost, the society may not be able to recreate what it once built. The Maya developed water management systems that allowed farming in areas that needed careful control of rainfall and storage. When those systems broke down, the land could no longer support existing populations. The resulting decline unfolded gradually, but was irreversible. Our modern civilization is far more complex than anything before it. The global supply chains that link continents make the trade networks of the Bronze Age seem simple. Our water systems use pumps, treatment plants, and computerized controls. Our food system depends on long-distance transportation and precise scheduling. Our medical systems depend on electricity, refrigeration, and communication networks. We have built extraordinary capabilities, reaching other planets with robotic explorers and splitting atoms to generate energy. But this same complexity brings vulnerability. It means we depend on continuous flows of electricity and information, and those flows can be disrupted by something as simple as a naturally occurring solar storm. The Norse colony in Greenland provides another meaningful example. Around 1000 AD, Norse settlers established farming communities in an environment that was harsh even under favorable conditions. They built homes, churches, pastures, and trading routes. Their society remained in place for about 5 centuries, but by the early 1400s, the colony disappeared. Excavations show that the settlers faced cooling temperatures, declining soil quality, and changing sea ice patterns that limited travel and trade. Instead of adapting their farming methods to the new environment, they maintained familiar European practices that no longer suited the conditions. They raised cattle in a place increasingly unsuited to grazing and continued relying on trade routes that became more difficult to use. Nearby Inuit communities, however, thrived. They had tools, clothing, and hunting techniques suited to Arctic life. As conditions grew colder, the Inuit adapted easily and remained stable. The Norse, who refused to change their methods, could not survive the shift. Their failure was not due to lack of intelligence or effort. It came from cultural habits that made flexibility difficult. This pattern raises important questions about our own way of life. Our systems are built on the assumption that electricity is always available. Our cities, water systems, communication networks, transportation grids, and hospitals all depend on a constant flow of power. When someone points out that this dependence is a vulnerability, the response is often quick dismissal. People assume a large-scale power failure is impossible, or that someone, somewhere, has already prepared for it. The Norse in Greenland likely believed their familiar practices would remain viable. They likely believed the climate would not shift beyond what they could manage. They likely believed that supply ships would continue arriving. Those assumptions held until they did not. Our difference is that we have information they did not. We understand solar activity and have records of past solar storms. We have engineering studies describing weak points in critical infrastructure. We know that events like the Carrington storm and the Miyake events are part of the natural behavior of our star. The risk is documented and widely discussed in scientific and technical communities. If our systems fail one day, it will not be due to lack of knowledge. It will be due to decisions not to act, hardening transformers, creating national reserves of critical components, improving grid design, and reinforcing communication networks all require resources. Those steps compete with many other priorities. The result is a continued dependence on systems that could fail during a major solar event. Future historians, if a stable civilization still exists to produce them, may ask why a society with advanced scientific capabilities did not protect its fundamental infrastructure. They may question why a nation that invested trillions in many forms of technology did not allocate a smaller amount to strengthening the electrical grid. They may wonder why a society aware of the Carrington Event and the tree ring evidence still assumed such storms would not occur within its lifetime. Or perhaps there will be no historians to ask such questions. A severe enough collapse, lasting long enough, could interrupt education and knowledge transfer, skills that sustain modern systems, power engineering, Semiconductor manufacturing, advanced medicine are not simple. They require decades of accumulated expertise. If the institutions that teach those skills fail for a long period, or if many experts are lost, the society that follows may not be able to rebuild the systems that collapsed. This has happened before. After the Bronze Age collapse, writing systems disappeared in some regions for centuries. After the fall of the Western Roman Empire, certain construction techniques and technologies were forgotten. A solar storm-driven collapse might unfold in slow steps, not as a single dramatic moment. People living through it might notice shortages, then longer delays, then isolated failures, then widening disruptions. Each step might seem manageable at first, but as the failures accumulate, recovery becomes harder. If the damage to power infrastructure is large enough and lasts long enough, each passing day reduces the chance of full restoration. This is not a prediction of doom. It is a scenario designed to motivate preparation. The goal is not fear, but clarity. The Norse might have survived if they had adopted Inuit practices. The Maya might have endured longer if their farming systems had been more resilient to drought. Modern societies can improve their chances by reinforcing the structures they rely on. The civilizations that disappeared before us offer important lessons. They show that collapse is possible, even for societies that appear strong. They show that complexity can turn into fragility. They show that environmental and systemic stress can exceed a society's ability to respond. But they also show that adaptation can make the difference between survival and decline. We cannot change the behavior of the sun. It will continue to produce solar storms as it always has. Some will be small, some will be large, a few will be extreme. We can only decide how prepared we want to be when one of those storms arrives. History gives us warnings. Whether we use them is up to us. The European Space Agency carried out an exercise earlier this year that received almost no public attention. The goal was to understand how a Carrington-level solar storm would affect a satellite launch operation. It was a controlled simulation designed to test response procedures, reveal weaknesses in planning, and measure how quickly different systems would degrade under extreme space weather. The results showed how limited our defenses truly are. In the simulation, the upper atmosphere expanded by nearly 400%, increasing drag on satellites and causing orbits to decay rapidly. Communication blackouts disrupted every attempt at coordination. Radar systems used to track debris lost accuracy as signals passed through a disturbed ionosphere. Without reliable tracking, the risk of collisions grew, making it possible for one event to trigger a chain reaction of debris creation. This exercise was not intended to reassure anyone or suggest that institutions have the situation under control. Its purpose was to highlight how unprepared human infrastructure remains for a high-energy solar storm. Yet it passed quietly through scientific circles without entering public discussion. Most people never heard that such an exercise occurred, and even fewer heard what the results implied. This pattern is common in the space weather community. The information exists, the data is public, and the studies are detailed, but the topic rarely appears in daily news or policy debates. Even though the threat is not theoretical, it is a physical process tied to the natural behavior of our star. Several reasons explain this silence. First, the subject is complex. Terms such as geomagnetically induced currents, ionospheric disruption, and magnetospheric compression are unfamiliar to most people and do not translate easily into simple explanations. Second, the events are rare on human timescales. Carrington-level storms do not occur every decade, so the risk can feel distant. Third, the nature of the threat is uncomfortable. There is no way to stop a solar storm. It cannot be influenced, negotiated with, or redirected. It can only be observed as it approaches. and its consequences can only be managed if preparation was done long before the event. It is easier for many to assume that experts have already taken action, or that a solution exists somewhere in the background. But the facts we do know paint a different picture. We know the Carrington Event occurred in 1859. We also know that a Carrington-class eruption in 2012 missed Earth by around 9 days. The rotation of the Sun placed the ejection in a harmless direction. Had the eruption occurred about 1 week earlier, Earth would have been directly in its path. Several studies estimate that such an impact in the modern era would have caused trillions of dollars in damage. Some analyses suggest recovery would have taken years. We also know the critical vulnerabilities in the electrical grid. About 2,000 extra high-voltage transformers operate across the United States. These devices cannot be easily replaced. Their production requires specialized facilities, long manufacturing timelines, and coordination with international suppliers. Most are built outside the country. Replacement times, under normal conditions, range from 18 to 24 months. The Federal Energy Regulatory Commission has identified roughly 30 transformers whose failure could trigger cascading outages. Some combinations of as few as 9 failures could produce a coast-to-coast blackout. What remains unspoken in public discussions is why, given this information, large-scale preparation has not been done. There is no national supply of spare transformers. There is no comprehensive hardening program for major transmission systems. The engineering solutions are well understood. The estimated cost of hardening the grid, including transformer shielding and improved grounding, is around $10 to $30 billion. In national terms, this cost is small compared to other infrastructure investments, yet the money has not been allocated. Utilities often argue that such storms are rare, that existing protections are adequate, or that warning systems give operators enough time to adjust. These arguments examine probability but overlook the scale of consequence. A transformer costs a few $1,000,000. A long-term blackout costs far more, both economically and in human impact. Some organizations have raised stronger concerns. The Congressional EMP Commission studied the vulnerability of critical infrastructure from both natural and artificial electromagnetic disturbances. Their reports were direct and detailed, noting significant weaknesses and recommending urgent improvements. Despite their findings, the Commission's work did not lead to broad action, and the group was eventually disbanded. Former members continue to speak about the risks, but their voices rarely shape national planning. Government agencies acknowledge the hazard. The Department of Homeland Security lists space weather as a significant risk. The National Oceanic and Atmospheric Administration operates the Space Weather Prediction Center, observing the sun 24 hours a day and issuing alerts whenever solar activity increases. The monitoring systems exist, but monitoring alone does not prevent failures. Being able to detect a storm does not mean the underlying infrastructure can survive it. This is the core issue that often goes unmentioned. The vulnerability is not hidden, it is known. Yet relatively little has been done to reduce it. Tree ring studies show that the sun has produced events many times stronger than Carrington. Engineering studies show that the grid would fail under conditions far weaker than those historical peaks. Economic studies show that the investment needed to harden the grid is small compared to the cost of a prolonged outage. The information is clear. The follow-through is limited. The large sunspot cluster now rotating across the solar disk may pass quietly. It may release only moderate flares. It may decay without producing a significant eruption. The most likely outcome of any given sunspot is uneventful, but the long-term statistical reality remains unchanged. A large solar storm will occur again. Whether it happens in this cycle or a later one cannot be predicted. What is predictable is that the infrastructure, as currently built, is not designed to survive the upper range of what the sun can produce. Some people wonder what they can do individually. Personal preparation can help in short disruptions. Storing water, keeping non-perishable food, owning battery-powered radios, and maintaining basic emergency supplies. Small steps like these can extend a household's resilience by days or weeks. But in a long-term grid failure lasting months, personal preparation alone cannot compensate for the collapse of national-scale systems. The electrical grid, fuel networks, food distribution systems, water treatment plants, and medical infrastructure are interconnected at a scale no household can replicate. Meaningful protection must happen at institutional levels. That includes utilities, regulators, and elected officials choosing to prioritize grid hardening, transformer reserves, improved response protocols, and research into better forecasting and shielding technologies. The knowledge to reduce risk exists. The choice to act on that knowledge remains a matter of policy and public will. The information used in this analysis is not classified. Almost all of it can be found in public reports, scientific studies, and government documents. Anyone who takes the time to look can find the data. The challenge is not a lack of information, but a lack of attention. Many other risks compete for public concern, and space weather often falls to the bottom of the list because it feels distant or unlikely. Yet the consequences of inaction could be far greater than many threats that receive more frequent coverage. This does not mean a Carrington-class event will occur tomorrow. It does not mean the current sunspot will produce such an eruption. The odds of any single region generating a major event during its Earth-facing period are low, but the long-term certainty remains. The sun will eventually produce a storm beyond our present capacity to withstand. When that happens, the outcome will depend on preparation completed years before. At this moment, the largest sunspot group in a decade continues turning toward the central region of the solar disk. Solar cycle 25 has already exceeded multiple early projections. Activity is higher than predicted. Forecasters are watching closely, analyzing magnetic structures, flare probabilities, and signs of instability. Each update reflects both expertise and uncertainty. The sun does not always follow its expected patterns, and now you are aware of details that many people never hear. Most people who depend on modern technology, and that includes nearly everyone, do not know how sensitive our systems are to solar activity. They may understand weather on Earth, but not weather in space. They may know that storms can disrupt flights or knock out communication, but not how far the disruption can spread if the energy is large enough. What someone chooses to do with this information is up to them. The information itself, once learned, remains. It becomes part of how one understands the systems that support modern life and the forces that can affect those systems. Across this exploration, we have followed the path from the surface of the sun to the infrastructure built on Earth. We examined the magnetic structures of sunspots, the physics of flares and coronal mass ejections, and the records preserved in tree rings that reveal storms far larger than any in written history. We walked through the first days of a hypothetical grid failure to understand how deeply electricity shapes food, water, communication, healthcare, and transportation. We looked back at earlier civilizations, not as direct comparisons, but as reminders of how complexity can become fragile under stress. The sun continues its activity without pause. Nuclear fusion at its core generates the energy that supports life on Earth. Magnetic fields build and shift above its surface. Plasma escapes into space in a steady stream and, at times, in powerful bursts. These processes have operated for more than 4 billion years and will continue for billions more. Our presence is temporary in comparison, yet the time we occupy is shaped by the sun's behavior. A sunspot may produce spectacular flares, and trigger auroras visible far from the poles. It may do little more than brighten scientific images before fading. Neither outcome changes the underlying fact that the sun is capable of storms far larger than those seen in the modern technological era. The infrastructure we rely on has grown faster than our defensive measures. Hardening the grid, stockpiling equipment, and improving response planning remain tasks that must be done before they are needed. If the sky is clear, a person may look upward and see the light of the sun reflected across clouds, buildings, and landscapes. That light enables life, drives weather, and powers nearly every ecological system on Earth. The same star also produces the storms that can affect electricity, satellites, and communications. Understanding both sides, supportive and disruptive, is part of understanding our place in the solar system. The sunspot will continue its path across the solar disk, and scientists will continue to observe it. The cycle will progress, measurements will accumulate, and new data will refine our understanding. The broader lesson remains steady. Awareness and preparation improve resilience. The storm that challenges modern systems has not yet arrived, but the capacity to reduce its impact is within reach long before it appears.